The other day, I posted a video about using YouTube as cloud file storage, and it kind of blew up. In the comments, one of you guys joked that maybe the video that you were watching was actually just a backup of my hard drive. And that got me thinking, if we could store files on YouTube, what if I just backed up my entire disk there? Or even better, instead of YouTube, what if I just live streamed my entire hard disk to Twitch for the world to see? Now you might be asking, why would anyone back up their files to Twitch instead of being a normal person and using Google Drive, Dropbox, or, I don't know, literally anything else? Well, it would be so much funnier if someone backed up their drive by streaming it on Twitch. You could even retrieve your data by downloading the Twitch VODs or saved stream recordings. Last time, the very first problem we ran into was figuring out where to actually hide our files inside the video. A video file is basically a digital container holding a bunch of different things: the visual footage or video, the audio, the subtitles, and some background text like authors or descriptions called metadata. But as it turns out, many video or streaming platforms strip out some of this data the moment you upload it. For example, video platforms like YouTube don't use most of the metadata fields, so they're usually automatically removed. Even subtitles aren't spared. Platforms might refuse to load the data since subtitle engines aren't designed to carry this much amount of data. That just leaves audio and video. If we do some quick math, we can see which one holds much more data. If we take standard CD quality audio, this gives us about 1.4 megabits of data per second, because it is 16 bits per sample and it has a 44.1 kilohertz sampling rate. If we take a full second of uncompressed 4K video on the other hand, this gives us about 4,800 megabits of data, because there are 3,840 times 2,160 or over 8 million pixels, each storing red, green, and blue byte data being displayed 24 times every second. This means that a second of an unprocessed 4K frame holds over 3,000 times more data than audio. But we can't just shove our raw computer files straight into those pixels and call it a day. To make sure your video or stream is playable on every device, from a massive 4K smart TV to even a Samsung refrigerator, video or streaming platforms have to heavily compress and transcode your video. To our human eyes, the compressed video looks identical, but under the hood, the exact color values of those pixels have been completely changed to save space. Because our files rely on that exact color data to survive, this would instantly corrupt all of our data. And since these algorithms are essentially a giant proprietary black box, we have absolutely no idea how the platform is going to change our pixels. Now you guys are very smart, and a bunch of you in the comments had the same idea. Why not just study the pixels before and after the compression to find a pattern? Or even better, why not train like some neural network to figure out what the black box is doing behind the scenes? This process is called reverse engineering, basically taking some program apart to see how it works internally. It's not just applied to our case, but also in cybersecurity to find vulnerabilities, archaeology to find when structures were constructed, or forensics to piece together evidence during a criminal investigation. It's even how, today, we're able to play some super old DVDs in your media player. Because back in 1999, some Norwegian programmers actually reverse engineered a fiercely encrypted DVD format. The issue with reverse engineering in this case is that, unlike the DVD format, streaming platforms are constantly changing their compression algorithms. It's not something that we can pick apart once, and uploading the same exact video twice might yield slightly different results. This is because of the nature of different video compression codecs, which aren't fully deterministic. Combined with this black box, there could be a million hidden variables we don't know, like server load, internal pipeline changes, or anything. What works today might silently break in a month when they tweak their compression algorithm. In other words, it's not easy to reverse engineer something that's constantly changing. That being said, instead of trying to figure out the system, we can find ways to work around it. In my last video, we took a look at a real-life example, QR codes. QR codes are resilient to scratches, tears, horrible printing, and anything, to be honest. They use an algorithm called Reed-Solomon, which automatically detects and usually fixes errors from rips and tears. Using QR codes for each frame of our data is super space inefficient, but we could apply the same error correction logic to our system by asking ourselves two questions. Has this data been corrupted by compression? And if it has, we still have enough redundant information to reconstruct the original data? For our first question, we can use a clever piece of math called a cyclic redundancy check, or CRC, to determine whether or not our data was corrupted. You can think of it like a unique fingerprint or hash. It's the same technology your computer uses to make sure a file doesn't break while downloading from the internet. If the platform's video compression changes even a single bit of our data, we will almost always get a completely new fingerprint. So by just checking that fingerprint, we instantly know if our data is corrupted. And while CRC is great at catching errors, the thing is it can't actually fix them itself. To do this, we need to use an error correction algorithm called Wirehair. Wirehair is a fountain codec which is super good at fixing errors when we don't know how much of our data will be destroyed in the end. In our case, we don't know how much compression will destroy our data, so we can treat it like a lossy noise layer. Wirehair steps in and generates a smart combination of repair chunks, almost like a system of equations. And then, when we want to get our data back, it attempts to solve these remaining equations for each variable or chunk of data to more reliably recover the original files. However, we still need to figure out how to actually encode this error-proof data into our video using FFmpeg, keeping in mind that the video or streaming platform will recompress whatever we upload. While we can't reliably determine what video or streaming platforms do behind the scenes in their pipelines, we know a lot of information about codecs, which is a part of their pipeline. Modern compression codecs break each frame into small 8x8 pixel blocks and convert them into frequency patterns using a mathematical operation called a Discrete Cosine transform, or a DCT. After this transform, the block is no longer stored as pixels, but as a set of frequencies, where the big number in the top left represents the overall brightness, and the nearby numbers describe general shapes, and the rest represent tiny details and noise. When compression happens, those tiny values get aggressively rounded away to save space. But the big important values survive because that's what our eyes actually notice. When encoding our error-proof data, we can hide the bits inside those big, stable frequency values, or more specifically, in the sign of those values. Video compression might change the magnitude or how large the number is, but it usually doesn't flip its sign, giving us a better chance and more reliable way of recovering our hidden bits. Many of you guys in the comments suggested using ranges for the bits. For example, maybe any value from 0 to 9 represents one piece of data, and so on. In theory, this sounds like a good idea because it would let us pack much more data into each block instead of just relying on the sign. But we have to remember that black box we talked about earlier. Because platform compression isn't 100% deterministic, we don't really know how much certain numbers will get rounded down. A value of 90 might get compressed to an 85 on one upload, but heavily rounded down to a 10 on the next. Since we can never really guarantee a safe range for these values to land in, we have to stick to the sign instead of the magnitude. Finally, there's one last detail before we actually upload this video, which is the export format. In my last video, we had a choice of picking between different video formats, and we chose a special video format called FFV1, which is lossless. This means that our data wouldn't get damaged twice, once during our local export and again on YouTube. Unfortunately, this isn't the case anymore when it comes to streaming. Many streaming platforms enforce a specific input codec, like H.264, that's lossy. This would mean that our data would get corrupted twice or more. But luckily, our error correction should be powerful enough to survive it. After all, many of you guys in the comments experimented with my tool and realized that the data is usually still intact no matter the export format, which is great news to hear. For small files, this entire setup worked perfectly. However, there's a huge difference between uploading a 50 kilobyte bscript file versus streaming an entire hard drive that could be tens or hundreds of gigabytes. From our last demo, it took several minutes to even export a few kilobytes of data, so it would take literal centuries to do an entire hard drive. So how can we make this much faster? Well, ever since my last video, I've been working on a ton of optimizations to speed up this whole process. One of the first and easiest upgrades was swapping our hashing algorithm. Before, we were using CRC, as I mentioned, to check for corrupted data. CRC is great, but it was invented in 1961, which is over 60 years ago. Modern algorithms like xxHash are much faster because instead of relying on complex sequential math that constantly waits for the previous step to finish, xxHash chops our data into smaller chunks and processes them all at the same time using CPU pipeline-friendly math like simple addition or XOR. You can think of it like a teddy bear factory. While CRC works like a single assembly line that has to sew the left arm, then the right arm, and then the legs in sequential order, xxHash has multiple assembly lines making the arms, legs, and head all at the exact same time before just stitching them all together at the very end. Making this one tiny change made our tool twice as fast. But the biggest optimization I made was parallelization. To understand why this is so effective, we have to look at how the CPU actually works. Most people think that their computer runs all their apps at the exact same time. The thing is, if you have a single core processor, you can still run many processes like Discord, Spotify, and Chrome at the same time. How? Well, in reality, the CPU is actually frantically switching between Discord, Spotify, and Chrome thousands of times a second to make it look like they're all running simultaneously. This is called a context switch, and constantly swapping all that data back and forth wastes a lot of time. But luckily, most modern CPUs don't just have one core. They have multiple, like 8, 12, or even more. And to utilize all these cores, operating systems like Windows, macOS, or Linux provide a tool called a thread. Instead of just using those cores to run background apps, threads allow a single program like our tool to use many CPU cores and force them to work on the exact same task at the exact same time. For example, let's say our file is divided into 64 chunks of data, and my computer has an 8-core CPU. Our old program was basically ignoring these extra cores, forcing a single core to process all 64 blocks sequentially. But by using 8 threads, we can partition the workload so each core has to process only 8 blocks. Because all 8 cores are now running in true parallel, we don't have to wait for chunk 1 to finish before starting chunk 2. Besides parallel computing, I also added a few other meaningful optimizations, like writing custom SIMD code and improving our memory buffering. While these optimizations are a little bit more technical and they weren't as impactful as parallelization, They still sped up our encoding and decoding loop a few times, so it's definitely worthwhile to mention. And at the end of all of this, I estimated that our entire process was up to 100 times faster than what we originally had before, which is absolutely insane. This speed up is going to help us a lot when we finally transition to working with an entire hard drive, which could be multiple gigabytes of data or more. So now that our encoder is officially fast enough to handle the payload, we need to actually build our hard drive. The original goal was to back up an entire hard drive to Twitch, but since I don't exactly have like a physical spare empty drive sitting on my desk to just plug in and use, I went with the next best thing, a virtual hard disk, specifically a VHDX file. A virtual hard disk is quite literally a digital clone of a physical hard drive. Instead of trying to stream a million loose files one by one, we can package everything into this one massive organized file. The cool thing is that your computer treats a VHDX file and a real physical hard drive plugged into your motherboard as the same thing. Stores the exact same folder structures, stores the file system, and all the raw drive data itself. Now some of you might be wondering, why don't we just shove everything into a giant zip file? Well, the thing is, a zip file is merely just a compressed folder and nothing else. A VHDX has a fully functioning environment like the boot sector, the file system, the operating system itself, and any other applications or user data you might have. So if you guys manage to download my Twitch stream and decode the video, you won't just get a boring folder with the B script, but an actual mountable drive that you can load onto your computer and boot up exactly as I left it. But before we even start adding data to this file, we have to decide which operating system to actually install. If you guys are actually going to download my hard drive, I wanted to have a system ready to go so you guys can actually boot it up. Now, we could use Windows or Mac OS, but modern versions of those can easily eat up 50 gigabytes of data between the pre-installed apps, random AI features, and telemetry. They're just too bloated for a Twitch stream. On the other hand, a Linux distribution like Ubuntu only needs around 10 gigabytes. We can go even lower with something like Void Linux, which fits in a single gigabyte, or TinyCore Linux, which is only 100 megabytes. That is literally smaller than the YouTube video you're watching right now, but I didn't want to choose something too bare bones. I still wanted this to feel like a real computer. Introducing SliTaz, one of the tiniest Linux distributions out there. The operating system is only around 100 megabytes, which leaves us plenty of storage for any other data we want to include. Despite how small it is, it actually looks decent. There's a completely functional desktop, and I can even play a game of chess on it. These types of operating systems use so little data that people often load them entirely into their RAM to make them run incredibly fast. To get this working, I'll start by downloading the SliTaz ISO file. You can think of an ISO file as a digital installation disk. I'll point my virtual machine towards that ISO so it can boot up and install the operating system directly onto our VHDX file. Once that's done, our virtual hard disk is officially ready for the stream. As for actually streaming our hard drive, we have to choose the right format for the job. There are several streaming protocols out there, but they aren't all built for the same thing. For example, formats like RTSP are what you will typically find in security cameras. They're designed to control and deliver media streams and surveillance setups, often using a subprotocol called RTP to carry the actual audio and video packets. However, for our system, we don't want to treat this like a static security camera feed. Most major streaming platforms like YouTube or Twitch use a protocol called RTMP, which is designed to send live video directly to a platform's ingest servers. This works perfectly for us because the moment our encoder produces a frame, we can package that output and send it straight to Twitch in real time. Once that connection is established, our hard drive is officially live to the world. Now, there's only one thing left to do. There's honestly so much I learned throughout this process. And that's my hard drive, not my actual one, but you know, the ones for you guys to download and mount yourselves. Once again, is this ideal? Probably not. I mean, it's likely against Twitch's terms of service, but is it cool? Absolutely. If you enjoyed this video, you'll probably like my previous video too. Code's open source, same repository, so you can view it in the GitHub link below. It's written in C++ and uses some libraries that you might have to install in order to compile it.